Hi, I'm Janine Cody, talking to you on our live broadcast from the Chromosome 18 Registry and Research Society office. And today's topic is based on a question from you all, as will all our topics be based on those questions. So keep the questions coming. And this week I wanted to talk about or answer the question about, is gene therapy a possibility for treating chromosome 18 abnormalities? And I'd really like to preface this discussion, and probably all of our discussions, by saying if we did not believe that making the impossible possible, then we wouldn't even be here. So if I say something is not possible, not doable, that's just today. It may change, and we hope it will change. So keep that in mind, that we're always trying to make the next best thing happen. So given that, back to the question, is gene therapy a possibility for treating chromosome 18 conditions? Well, first of all, it really depends on your definition of gene therapy. If what you're thinking of gene therapy is taking that missing chunk of chromosome and putting it back in all their kids' cells, or taking that extra chromosome 18 and removing it from all of their cells, that just sounds like a fabulous idea, because that would just be the answer. That's the problem. That would be the fix. It'd be a one-stop fix, and all would be well. But there's some issues with that. So first of all, getting a chromosome into or out of a cell, chromosomes are really big things, and relative to the size of the cell, and they're highly packaged within the cell. So getting a chromosome into or out of a cell is really like you or I trying to enter a room through a keyhole. And so we have a big issue regarding size. So that's one major obstacle. The other obstacle is that this would have to happen to every single cell in the body. So how do you achieve that? At the moment, there's ideas for getting single genes, into a limited number of cells that might be accessible because they're in your lungs, or accessible blood or something. But getting it into every cell in the body at this point is not feasible. And the other problem with this single solution would be you'd have to get that piece of chromosome into the right place in the genome. You can't have it just inserted somewhere else. It could cause a new problem. And to remove a chunk of chromosome, you'd have to remove exactly the right piece, no more, no less, or you'd have another problem. So, so that's another issue. And almost everybody has a different duplication or deletion. So this would be a individualized therapy for each person. So the one-step method or approach to gene therapy, just removing a whole piece of a chromosome or a whole chromosome, or adding back a whole piece of a chromosome, has just major obstacles at this point in time. So what gene therapy really is good for, or starting to be used for, are single gene disorders. So remember, chromosome 18 has 263 genes. So a single gene disorder involves a single gene. So gene therapy is being used for much smaller issues, genetically speaking. And mostly what it's being used for is adding back key genes. And a good example is cystic fibrosis, in which it's a recessive condition. So that means that the person with cystic fibrosis inherited one non-functional gene from each of their parents. They have no functional copies of the CFTR gene at all, zero, none. So adding back a gene that becomes functional and gets into just a few of the cells in the lungs, it may not be 100%, it may be 20%, but that's probably good enough, because it's a lot more than zero. And so gene therapy is used mostly at this point for single gene disorders and conditions not like ours, conditions where there's nothing there at all and they need to replace it with a gene. In our case, our kids already have 3 copies instead of 2, or 1 copy instead of 2 of perfectly normal genes. So what we're looking for is a treatment that's a little more nuanced. And it's not just something is good enough, it's that they have 50%. We add back some, but we can't add back too much, because if you add back too much, you might cause the symptom of trisomy 18 in someone with 18p minus, let's say. So it's a much more delicate and nuanced situation that we're faced with. And there's been a lot of news lately about the CRISPR technology, which is just amazing, amazing technology. And what that is a technique to correct misspellings in a gene, or create misspellings if you're trying to make a mouse model or something that recapitulates a disease. But it's also starting to be used for making gene deletions. And at this point, deletions can be as big as a small gene. So that's interesting and hopeful. And also it can be used for making insertions of genes. And the largest insertion sizes at this point are still a little small, but people will figure that out and they'll get bigger. So the day will come when maybe entire genes can be inserted using CRISPR. However, what you need to understand about that is that these techniques are done in single cells. Stem cells or an embryo, and so the correction, takes place within a single cell. They might do this for 100 cells, pick out the 2 or 3 where it's successful, and then those would be implanted in a pseudopregnant mouse and become mice. So they start with a single cell and create the CRISPR edited mouse in this case. So what we're faced with is people that are already born, not embryos or stem cells. So that's one way where our situation is a little less directly related to how CRISPR could help. But the way it really, really could help us a lot is in making mouse models. So one of the things we've been doing in the last few years, and many of you may know about the knockout mouse project that we've started with a couple of different genes, and the data is being analyzed. Mice, they're called knockout mice, have deletions of individual genes. And so they're available for most genes. Sometimes it's only an embryo that's available and you have to mouse grown up, but they are available. With CRISPR, we can not only have deletions similar to a knockout mouse created, but we could theoretically have single genes inserted back in to see what the effect is of one single gene being inserted. We could also, even more exciting for me, because I'm beginning to appreciate that some of the issues that we see are caused by the additive effect of 2 genes missing that work together to create a problem, or 2 genes duplicated that work together to make a problem. And so with CRISPR, we could delete 2 different genes in the same mouse, that genes that are not right next to each other but very close. And this would be almost impossible without the CRISPR technique. So this holds great promise for our mouse model experiments. And that's really important because with mice, we can look at their brains, we can look at their physiology, we can see how they age, we can measure the biochemistry, we can do all kinds of measurements in mice that you can't do in people to really understand what the effects are of a missing gene or duplicated gene. And then when we understand that, then we can begin to use different compounds, drugs, or drug prototypes to reverse those effects in the mice. So the mice are really critically important, and CRISPR is really going to help us take this next step into understanding the effect of multiple gene deletions or duplications. So that's where it's really, really going to be important for us. So back to the original question, is gene therapy a possibility for treating chromosome 18 conditions? It's definitely, the technology of gene therapy is definitely going to be helpful for helping us understand the conditions. But for treating people with chromosome 18 abnormalities, again, I've already sort of mentioned, the big problem is we're talking about existing people. And there's not a method for direct delivery of corrections into cells. At the moment, that's not within the realm of possibility. And the other thing we really have to remember here is we're correcting the effects of having one gene instead of two, or 3 genes instead of 2. And so whatever we have to do, whatever we do has to be very, very precise. Not too much, not too little, because we already know too much and too little is the source of our problems. So, so that's one issue with the therapy route. But the other part is, imagine we do have a gene therapy that is for the cells in the gut, let's say, and we're able to deliver the altered genes to those cells, but those cells don't last forever. They don't last for the life of the person. They turn over. So in a certain amount of time, you'd have all new cells that had not benefited from the gene editing, gene therapy. So gene therapy would have to be something that would have to happen over and over again. So, so that's an issue with the therapy side of this. And of course, reversibility. Doesn't matter what we do, gene therapy, anything else, it's going to have to be reversible as sort of a due diligence sort of approach to making sure we're doing the right thing. So in summary, gene therapy as a direct therapy for our kids is a very long ways from being possible and useful, but the techniques that have been developed because of gene therapy and are used in gene therapy, like CRISPR, are really going to be important for us in the future and future experiments. So let's see, with that, I'm happy to take any questions. And before I forget, I want to be sure to mention that next month, on the 18th of the month, Dr. Catherine Larson will be talking about tips and tricks for dealing with anxiety in our kids. So I think a lot of you know Dr. Larson already, better known to most of you as Kat. So she'll be here then. And then after that, we are dependent on your questions. So the more interesting your question, the more interesting the live broadcast. So I hope. And we're always interested in your feedback and your questions. So let's see, I don't see any questions. I forgot to tell people to put questions in the chat box, but I think most people are more computer savvy than I am, and they know a chat box when they see one. So, do we have any questions? No. How does the therapy take place? That, the specifics, well, it's not really possible, so I can't really tell you how it would take place. It would depend on what organ we were trying to treat. So if it was the lungs, you might inhale a virus or something. If it were the gut, you would need to, ingest something. I think I just read something about, I think it was a gene therapy where the people had to have an injection into their spine, the spinal fluid, to get the gene therapy to the brain and to the spinal cord. So it just depends on what. So there's a lot of depends. It's a very broad technique. It's kind of like saying, how would you deliver a medicine? Well, it sort of depends whether it's what kind of medicine it is, something you inhale or something you swallow. So, gene therapy. Oh, never. We don't have any gene therapy. Yeah, that was sort of the point of this, I guess. Sorry, I didn't make myself clear. There aren't any gene therapies. The problems are way, way bigger than what we're going to solve in a few decades. But where those techniques can help is in developing the mouse models that will help us learn more about the chromosome 18 conditions.
So you talked about CRISPR mouse method. Can you explain a little bit more about that?
Not in 15 minutes. That's sort of my issue here, is how to do something in 15 minutes. A CRISPR is basically molecular scissors that are very, very precise. It's a brand new technology. It's like every lab can do it. Pretty much every lab is doing it because it's very straightforward, simple technique of molecular scissors to cut genes, cut out, make corrections, correct misspellings in genes, or to create small deletions or duplications. So, okay, with that, I think we'll close because our time is up. And looking forward to answering questions. We can answer questions by email if it's a specific question, or we can have another broadcast in what would be March. So, oh yeah, that's right. Go to River and ask questions because those come to me and I can attempt to answer them, and you can chat among yourselves. So River is really going to be a helpful conversation platform for us. So thank you so much, and we'll see you with Dr. Larson next month.